Hi everyone, my name is Mitchell Dowdy and I'm currently a fourth-year PhD student at the University of Toronto. I'm excited to share my recent work with you today titled SurgeonAssist-Net towards context-aware head-mounted display-based augmented reality for surgical guidance. Augmented reality combines virtual and real-world elements and has been used across numerous medical domains for training as well as for surgical guidance. Its main benefit is that it's able to eliminate the disconnect between a screen and the surgical scene and has been shown to enhance task performance when effectively implemented. On the left, this is an example of the HoloLens 1, which is a type of optical see-through head-mounted display. On the right, we can see an example of a very crowded user field of view here with way too many virtual augmentations. And in this case, there are concerns of distracting the user and actually resulting in reduced performance over typical guidance techniques. So far, the bulk of research work has centered around technical developments, these being achieving certain accuracy or speed metrics. However, this doesn't guarantee the effective transition of these guidance systems to clinical practice, and really this is evidenced by the lack of clinically available head-mounted display-based guidance systems. When we talk about effective AR-based guidance, what we mean is trying to understand what the user's intent is and provide relevant information for that surgical task or action. This is done through context-aware surgery, which begins with extracting features from video data or from robot kinematics, using signals and cues from those features to interpret the task through some sort of predefined model. We can arrive at a prediction for the surgical task and potentially use that information to improve upon guidance. The challenge with previous approaches is they've remained limited to applications where video data is readily available and have relied on large computational resources in order to achieve performance with no real focus on real-time implementation. So in contrast to these systems, we want to provide online context-aware virtual assistance to the wearer of a head-mounted display. Our network is as follows. We begin with a sequence of 10 input video frames, then feeding to our Efficient-Net Lite backbone. We grab features that are relevant from the data and feed those to a gated recurrent unit, which learns temporal dependencies about that input video sequence. After that, we feed it to a dense convolutional layer, and we're able to extract our predicted task from the input sequence. The details for software implementation on the HoloLens 2 are available on my GitHub repository online. The two datasets we make use of are the Colic 80 dataset, shown here. This is for laparoscopic surgical tool and task prediction. And on the right, the user-centric surgical task dataset, which was created in-house and incorporates 5 different basic surgical tasks recorded from the HoloLens 2 point of view. Looking at the results of our approach versus current state of the art, we can see that we outperform them both in accuracy and in speed, as well as latency, meaning that our model, alongside its compact approach, can operate on a commercially available optical see-through head-mounted display. On the right is an example of online inference with our model. Shown is the current prediction, as well as the ground truth prediction and the inference time required for prediction. Looking at results on the user-centric surgical task dataset, it's a very similar story to before. The difference here is a 5 times decrease in CPU inference time after exporting our model to a more efficient format and one that's required for uptake of that model on the HoloLens 2. We envision 3 different tasks or general classifications for clinical use cases for our system. On the right, I'll highlight the training use case, which is to reinforce learning with information that's relevant to the current task. So you can see here a user is going through a set of predefined surgical tasks. They're wearing the HoloLens 2, and as they're performing those tasks, the SurgeonAssist-Net is detecting the current task of the user and updating this user interface showing the prior tasks and the upcoming tasks that are performed. So in conclusion, we presented a framework that's capable of understanding user-centric activities and providing online real-time workflow assistance to the user. Our approach competes with state-of-the-art solutions and is able to be run using the computational resources of a commercially available head-mounted display, in this case, the HoloLens 2. For future work, we envision a more in-depth user study to evaluate a manually controlled AR approach versus a context-aware approach, would be very interesting, along with the collection of a larger user-centric training data set with more realistic surgical tasks and actions. Thank you very much for listening.